Okay, so on the mean value theorem, it's about parallel. Mean value theorem is all about same slope. It's all about being parallel, and they may not even ever say mean value theorem. They may not say MVT. They may say find the rate of change from like 0, 1 to 4, 8. And so you just find like the Cumming slope, y minus y over x minus x, which we constantly call the difference quotient. Okay. Then on the B part, they might say find the equation of the tangent line that's parallel to this secant line. Okay. So what might be happening is you might have a graph that goes from 0, 1 to 4, 8. And do you see you found the average rate of change? They say average rate of change. They won't say crummy slope or average slope. They'll say average rate of change, okay? And so you found, they may say find the slope of the secant line that connects the two endpoints, okay? So you found the slope. And if only it's differentiable, do you go forward with the mean value theorem, okay? So watch for that if I put questions in there like which one must be true kind of problem. So say they've given us a question, and by the way, if they say it's differentiable, by default it's what? Continuous. If the graph is not differentiable, you should not go forward with the mean value theorem, okay? Because you could have something like this, and it's not differentiable or possibly not defined somewhere. Do you see that there never is a time on this domain where those slopes are the same? Does everybody see that it's got, I'm never going to have that slope. But the point of that was it differentiable, okay? So if the f of x I give you, you would take the derivative. You would take the derivative and set it equal to the slope that you found. You might get more than one answer. If appropriate, you just let the algebra take course. And make sure that you are actually given the answer like in the domain. It could be that I run into a quadratic and it tells me two numbers within 0 to 4. Or it could be something like you're only looking within that domain is what I'm trying to say. So if you think about like a sine graph, it goes up and down and you don't need to go outside the domain that they give you. You just list the points in that domain where it's satisfied. It has to be continuous and differentiable. So the corollary to that is Rolle's theorem, but you don't really have to know that. It'll just happen naturally, kind of organically. With Rolle's theorem, what would happen is that f of A would maybe be 7, and f of B might be 7, so that when you take the difference quotient, what number do you get? The slope would be what? 0. So if you know that all of a sudden you have a slope that's 0, it could even do this. Well, no, it couldn't. Because if these are going to be the same, it's got to come back to where it started from, right? And so just kind of like an added emphasis there. If your slopes are the same, if your values are the same and your slope is 0, your average slope is 0, that means if it's differentiable, not only does it satisfy mean value theorem, but that point is a critical number. But again, I just want to go over it again. That should make logical sense. If you're setting a derivative equal to 0, you're also looking at critical numbers, and that's what Rolle said. Oh, but wait, if f of A equals f of B, the number we find that's parallel to that would also be a critical number. Okay? It could be that somebody finds a specific number of problem that we want to do, but make sure you practice the mean value theorem worksheet, and I gave you some problems out of the book. Okay? If I have something like this, f of x is equal to 1 over x minus 4 on the interval from 5 to 7, I go forward. Okay? Probably. It is continuous from 5 to 7, right? And then if I take the derivative to see if it's differentiable, it's going to be -1 times x minus 4 to the -2 times 1. So I get -1 over x minus 4 squared. Okay? And if it's also differentiable on this integral, isn't it? And when you're doing mean value theorem, you're gonna need the derivative anyway. You've gotta see if it's differentiable, and if it is, then you set them equal, you set the slopes equal. If it had been on this domain, watch out for it. Game over, don't even work the problem. It's not even continuous, okay? Alright? So watch out for that. Now, it's only gotta be, I gave you an example a few classes ago where why the theorem said what it did. I just have so much trouble scrolling up.
Try going in full screen.
Oh, is that what happens? Okay.
Yeah, it might not work though.
There it is.
There it is.
There it is. All right, thank you. Yeah. Okay, so I gave you one that was sort of like this one time. Square root of x plus 2. And the domain was like maybe -2 to 7. And so if I find f of 7, I get 3. If I find f of -2, it's fine, I get 0. It is defined on that interval, okay? Then when I find the derivative, which I'm gonna need anyway, 1/2 times x plus 2 to the -1/2 times 1. So that gives me 1/2 square root of x plus 2. It only has to be differentiable on the open interval. If you look at the theorem, so you can still go forward. Do you see this is not differentiable at -2, but by the theorem you continue on. Is that okay with everybody? It has to be continuous on the closed interval and differentiable on the open interval. It has to be continuous on the closed interval and differentiable on the open interval. I've gone this far, let's work the problem, okay? So I'm gonna say 3 minus 0 over 7 minus -2. That gives me 3/9 or 1/3. So then I'll force my derivative to equal this. So I have 1/2 square root of x plus 2 equals 1/3. I would say at some point you're setting your derivative equal to 1/3 so that we know that you've done the mean value theorem. But quite honestly, on a free response, you want to make a statement that f of x is continuous on -2 to 7 and differentiable on the open interval. You want to let us know that you're smart enough to check that before you work the problem. Now, let's solve for x. Let's just continue on. So I just made this up. We'll see what happens. 2 square root of x plus 2 equals 3. So the square root of x plus 2 equals 3/2. When I square both sides, I get x plus 2 equals 9/4. Positive 9/4. That's kind of like a negative. And then when I subtract 2, I think I get 1/4. Does that look like that to you?
Yeah.
If I need the other coordinate, which quite often you do, I always fill it back into the original. So if I fill it back into the square root of x plus 2, I think it takes me back to 9/4, doesn't it? Sorry, I moved really fast in here. If I put it into the square root of x plus 2, I'll have 1/4 plus 2. 1/4 plus 8/4 is 9/4. So I kind of felt like I went around in a circle there, but that doesn't always happen. So now if they ask me to graph it or something, which a lot of times they do, and it's usually just to help us. We'll see, I have -2, 0. And 7, 3. Always mark off your units if you're drawing a graph. They almost always give you a place to draw it. The slope of the secant line, they may even say write the equation of the secant line, but there it is. And then can you see as I go from one to the other, there is going to be a time where it's 1/4, and I mean where it has the same slope, which is 1/3, and it happens at 1/4, 1.5. So my graph's not very good here, sorry. But you realize the times that you did your homework, a lot of times they have you type it all into your calculator, and you see what's happening there. Okay. So it's all about at some point, if it's differentiable, you actually put that slope. Okay. That mean value theorem rolls there. Okay, but really just mean value theorem is all you need to know. it happens that they equal the same thing, either by accident doing Rolle's theorem or by coincidence. All right, now let's talk about first and second derivatives. And I think those graphs really, I wanted to give you bunches of those with the threat of a quiz hanging over your head, but you would really, really come in today with a big, huge understanding. Those graphs make you understand the interaction between the first and second derivative. I'm going to work at least one of them for you where you can choose. By the way, for this test coming up, some of you emailed me about the last one, the Descartes. I heard lots of discussion about that from people. That last thing, I just sort of like let it stay there. It's one of those things that sometimes I forget to omit because you don't know how to do it yet. But this time, that's about where we're headed, so I thought I would just let you think about the Descartes. Like, how would you know that it was the absolute
answer
max?
though, and it made a lot of sense.
Yeah.
So I was like, yeah,
And
sure.
we're headed there, but that will not, figuring out which one went further than the other one is not gonna happen right now. That'll happen after.
That would have been my guess, but I have no idea how to do it.
Well, I'll teach you.
When you graphed it, it was.
Okay,
Yeah.
it is somewhat intuitive, but I think those of you that read the thing, you realize there's gotta be more to the concreteness
Yeah.
of that than what was said there. In fact, I wouldn't even have said what they said exactly, but we'll talk about that later. Okay, so, first derivative, is for finding increasing, decreasing of the original, relative maxes and mins, that come from your critical numbers. That's the first derivative test. If I have a picture, you'll see me work one of the ones I gave you, or we can pick a new one if you understood all of those, you got all the answers to them. I get away from the picture as fast as I can. I don't care if they give me the original, the first derivative, or the second derivative. If I'm looking at the first derivative, I'm going, oh, this is increasing, so this derivative has to be positive. If I see a first derivative that's positive, I think, oh, well, my original has to be increasing, okay? And then I can also look at the second derivative, but we'll get to that. The second derivative can actually test your critical numbers. There's two ways to test your critical numbers, the first derivative test and the second derivative test. The first derivative test is one of those plus minus charts that you actually have to write words about. The second derivative test is a fill-in of your critical numbers. So you can, and sometimes you can pick and choose. I made the test out yet, but sometimes it's forced on you, like use the second derivative test. I think a lot of you have learned that I want to use the second derivative test when it's really easy to take the second derivative. They're like 3x cubed. I'm not gonna want to, I could do a plus minus chart, but it's also nice to do the second derivative test. By the way, on that one, the second derivative will fail, now that I think about it, I'm going to go back. So the first derivative, how would the second derivative fail? If you get 0, that means you don't really know anything yet. You've got to go back to the first derivative, okay?
So why did you do it in the first place?
Because if you've just taken one of those ones that we talked about this morning, well, no, that's not when I would want to do second derivative. If you've just gotten through like a horrible quotient rule, I don't want to go into the second derivative test unless someone makes me, because it's going to be just as bad as the first derivative. But if I have something like this, say I'm doing a related rate problem, I wanted a maximum amount of water in the tank, and I have like a spherical tank, and dAdt is going to be 4 pi r squared dr dt. I don't know. I don't really want it to be a related rate problem right now. Sorry. That would have confused you when I think about it. Let me talk about it this way. Suppose you know the volume of water in the tank is a sphere, is spherical, 4/3 pi r cubed. Then V prime is 4 pi r squared. And then if you want to know you put the maximum volume, you would just so easily take the second derivative. Like a lot of times even the second derivative is a constant, and things always concave up or always concave down. And so sometimes I want to go on into the second derivative so that I don't have to do a plus minus chart with something. This is probably not a good example because it'd be easy to do either one with this one. Okay? So I probably shouldn't be making up some. But I'll look for some and we'll see. Also, you better know the second derivative test, because they'll, say, using the second derivative test, or sometimes they'll give you the second derivative and ask you about maxes and mins, okay? So I'll come back to that in a minute, but you can test critical numbers with the, second derivative using a fill-in. You can also find your possible points of inflection, but you better see a sign change before you call it a point of inflection. You better see a sign change in the second derivative. You can also find concavity, concave up and concave down, okay? Now, I'll get to you just a second. Now, your second derivative is actually the derivative of your first derivative, right? So you actually can use those to find out things about each other, never mind the original. Sometimes I have a second derivative chart, and underneath it I have notes to self about the first derivative, and underneath that I have notes to self about the original. One more thing, if you're really wanting absolute max and min, you can fill in your endpoints and your critical numbers, and you're just doing like a little evaluation. Doesn't have to be a chart, but list. Because you flagged like these as being highs and lows, and you just want to make sure your endpoints, maybe they're higher or lower than the bumps in your graph. All of this you're looking for where your first derivative is 0 or undefined. And for both of these, 0 or undefined. Both of those, I would just say, are red flags to us, but to me red flags usually mean bad things, okay? But it's like waving, look at me. Sometimes the critical numbers will not max your min. Like the graph will increase right through it, like this. But not always. At least they'll get the consolation prize. If they are not a critical number, don't be surprised if that same number shows up. Maybe it's going to be a point of inflection. But you better test it for a sign change, okay? So you don't ever call something a relative max or min without saying it changed from increasing to decreasing. Don't ever say something's a point of inflection without a sign change. They'll be sort of tricky to jump to that and always wait and see. Okay, I showed you a problem like that in the last class where I just flat out gave you the second derivative. And when I did a plus minus chart, I found all the zeros of the second derivative, but the signs didn't change on part of the chart, so that means the concavity did not change. Now, one more thing here and then we'll go to specifics. If I take the second derivative and I'm filling in one of my critical numbers and I get a number greater than 0, that means my graph is concave up, and so that means that critical number is a relative min. And if it's my second derivative is less than 0, it's concave down and I have a max. I almost always have to draw myself a little picture. My second derivative greater than 0, I go back to literal, like literally means it's concave up. Then I'll look at it and go, oh, that's a min. Something about that sign messes me up. Something else just flew through my head I need to talk about. Second derivative, filling in.
For the fill in, you fill it in.
Oh, you had a question. I'm sorry, go ahead.
I was just verifying for the fill in. You wrote that you fill it in. It's like add like.
You go back to the original. Because you may have this list of numbers. Like it might go from like -1 to 7. And you found some critical numbers at 3 and 5. And what Caitlin and I were just talking about, so many things can happen in this scenario. You found your critical numbers from your first derivative, okay? And you may have even tested them either one, and all you know at that point is a relative max or min. If somebody asks you for absolute max or min, then this could happen, like say this is a max, and this is a min. You better test your endpoints because you see like that was a max, but it also would have shown up, it wouldn't have shown up as my absolute max. So you can tell from this listing here which one's really the highest and the lowest. Okay? Be really careful if it's not defined in the original. But I've taught you to make notes to self about that too. Like Still, you gotta look at it in your charts, but don't call it anything that's not there. But things might change around it, you know that. If you have an asymptote, things could change concavities, increasing, decreasing. So put it in your chart, Xing it out as a note to yourself, you can't call it. Okay? Question, Carla?
Well, Elena and I have to go.
Okay.
We have a meeting at Parliament.
With college?
No, it's
No.
graceful leaders.
Okay. Wow. They get you out of classroom?
Have fun.
What?
They get you out of
Well,
classroom?
the meeting's at 12:10, but Miss Adams was like, the bus is coming at 11:30.
Okay,
So,
well, you might, if you feel like you need more examples, you can watch the end of the video,
thank
okay?
you.
All right, so I wanted to spend a little time today, and don't forget to go back and study related rates. I'm not gonna go over that today. You have video after video to look at from probably myself and Professor Leonard. Sheets that you can practice and problems that you can practice. If you want more problems out of the book, be careful if you go to the review, because we're stopping at 3:6, and chapter 3 goes on and has like 9 sections. So you might be, if you're at the review, oh, I'll tell you what, if I remember correctly, oh no, it doesn't. I was thinking already you told you what section it was coming from, but it doesn't. But anyway, you could easily work some problems out of the book. Let's go to, like you may think, but I haven't even given you something from 3.5, and well, let me say what 3.4 is. 3.4 is concavity in the second derivative test. You probably have bookwork and worksheets on that, and that's in your mind where we stopped. Okay, but 3.5 is limits and infinity. And I'll show you how that comes into play, but I definitely have gone over limits and infinity. As you're approaching like 3, does it go to positive or negative infinity? It helps you with what we call this curve sketching, all right? And then 3.6 is a summary of curve sketching, but I did that over the top with the worksheets you had to plow through over the weekend. That's curve sketching, okay? Well, let me show you one. Let's start with the problem, and don't panic, like, I'm not doing anything new. I'm just picking a problem that just really is gonna talk about all the stuff we need to know about first and second derivative and how it attacks. And everything I know about a graph, depending on what they ask me. You know, they could ask me for domain, they could ask me for asymptote, they could ask me for anything that you've learned up until now. So you have y is equal to x over, I'm just pulling this out of a good example in the book. Let me read the instructions to you. I think it says, analyze and sketch the graph, so they aren't very clear about that. But you know, on the AP test, they'll have, and which I'll cut and paste into your test, they'll have very clear directions. Suppose they say, oh, this is really cool, so I hope they watch the rest of this video. Things I need to know about this even before I start, if I'm going to sketch this graph, is its domain. Its domain is all real numbers, isn't it? Okay? Because I can't let x squared plus 2 equal 0, but I would tell the reader, which is me right now, I check that. Let them know how you know that. It's never 0, so the domain is all reals. Okay? So that's helpful. Also, problems like this quite often have asymptotic behavior that I need to know. And quite often under free response, they're not just going to let you out there to swim around with no direction. They probably will say, what are the, identify any asymptotes. This has no vertical asymptotes and no hole in the ground because they just led me down that road, but bottom's never 0. What do you think about the horizontal asymptote? No, good thought.
No, it's just 1.
No, but it's a square. So
Yes. No.
No, it's linear. It's.
Okay, so Grace has identified 1. Okay? Because remember how we cover up all of this? And you're more on the right track. We're going to add that piece to it. So you should always be like wary of absolute value and square roots. Like, I better be careful with this. To do horizontal asymptotes, most of us teachers cover up with, we say that fades in insignificance as I go out and look at the big picture. Okay? But I would tell them as a calculus student, then I'm looking at this as x approaches infinity and the limit as x approaches negative infinity. Okay? Remember me holding my arms out like this for horizontal asymptotes, okay? Horizontal asymptotes as I've gone out to infinity and negative infinity, where quite often the horizontal asymptote is just the same thing both ways, but it could be, I've seen 2 or 3 horizontal asymptotes, probably just 2, I don't think there could be 3. There could be lots of vertical asymptotes. Anyway, as I go to positive and negative infinity, you want to say that, like I know calculus, that's how I tell you, if it gravitates towards something, I have a horizontal asymptote. A vertical asymptote would mean I've come closer and closer to 2 and I was taken off to positive or negative infinity. Should look at it from the left and the right. Vertical asymptotes, you're coming toward a number, get pulled to infinity. Makes sense, right? Horizontal asymptotes, you're going to infinity and get pulled toward a number. It's a-okay for graphs not to have any of that or some or both or whatever, okay? Now, if I'm going to positive infinity, okay, let's go back to what Morgan noticed. I don't really care if I'm going out to infinity about that 2. Do I? If I have $9 billion and you go, well, here's 2 more. Okay? I found $2 in the wash this weekend when I was getting out of the dryer. I was pretty excited.
I found $20 in a pair of jeans.
See, that's a great thing when you're a mom. And to your kids when you do the wash. Whatever's in there is yours. Your husband's, your kids. Of course, it probably came from you for your kids.
Yeah.
But if somebody else gave it to them, it's like mine now. So anyway, square root of x squared. Does everybody understand, even in spite of silly stories that I tell, that the 2 is insignificant? Okay? And so what have we talked at length about the square root of x squared is? Before that, yes, Grace, it is plus or minus x, but it's the absolute value of x. Alright, so I'm looking at this, like if I go off to infinity, what's the absolute value of x gonna be? I'm sorry, we have this basically. Alright, so I'm just like talking out loud right now, okay? So do y'all understand if I'm going to positive infinity that it sort of turns into this?
Yeah.
Okay, if I put in a positive number like 1,000, this is going to be 1,000 over 1,000. What does absolute value do to those positives? Absolutely nothing. So that the one to the right gravitates toward 1. And a lot of people will just pick that one. But as you go to negative infinity, what's this going to be?
Negative 1.
It's going to be negative 1. And y'all done that some. You know, so always think of that. So you would always say my horizontal asymptotes, you know, identifying y equals 1 and y equals negative 1. In calculus, you really state the limit, all right? Y'all okay with that? I don't know what's happening. All right, so,
We're doing end behavior.
okay. I'm sure there's a wonderful dance that goes with that. All right, so now I have a horizontal asymptote at 1 and a horizontal asymptote at negative 1. Square root of x squared led us there, plus or minus and all that. All right, now let's do the first derivative and find increasing, decreasing, and critical numbers. All right, so I'm going to erase this so we can still look at the screen. That y'all can envision those being maybe A and B parts to get you started. Remember the one I gave you in groups one time for bonus? You know, it had like this A and B, what are the asymptotes and everything. All right, now, so y prime equals low d high minus high d low over low low. Okay? So this is a great problem because I got the quotient and the chain rule going on too. So it's a lot of review. All right, then cleaning it up, if a couple of things. If they say something like find the f prime of 3, don't do anything else with this. Just start slamming 3 into every x. Do y'all see what happened here? Please don't clean it up if you have a number to fill. But right now I'm looking for critical numbers. So I'm going to go through my 3 steps: negative exponent, common denominator, factor. This negative exponent just pops down underneath that. It doesn't go all the way down. So you do this very calmly. Negative exponent. Watch out for your negatives and everything. Does that make sense to everybody so far? It just pops down underneath what it's attached to. So you do negative exponent. Your next stop is common denominator. And I don't really mean the biggest common denominator. I mean the one I want to get rid of, which is the square root of x squared plus 2. So I'm going to multiply the top and the bottom by that. So I'm going to multiply this by the square root of x squared plus 2 and this by the square root of x squared plus 2. I'm not going to go through the angst of getting the chore of getting a common denominator. I'm just going to get rid of the denominator that I don't want. All right, this gives me x squared plus 2. This gives me minus x squared over x squared plus 2 to the 3/2 power. Are y'all okay with that? All right, and I'm just pick one out of the bottom. Let me see. Oh, they didn't. All right, so, oh, I just have 2 over. 2 over x squared plus 2 to the 3/2 power. All right, so my first derivative is always, just sticking to the board down here. All right, so the first derivative of this is always greater than 0. So I mean my function is always increasing throughout its domain. I had no critical numbers pop up. There's nothing that makes that 0 or undefined. So now let's go into the second derivative, okay? But let's pause. I'll use this problem as this example since it's kind of late. Back to Morgan's question. Suppose that I had gotten a critical number. Let's just say x equals 0 is my critical number. I have 2 choices now. They test it unless they tell me to do something. I can either do a plus minus chart right now with the first derivative, or I can take the second derivative and fill that number into it. I would not want to do the second derivative unless someone asked me to do it. Do y'all see here? I would choose a plus minus chart. All I had to do was test my critical numbers, increasing and decreasing. Okay? However, I want to know points of inflection and concavity. Say that's the C part of my question. So always tell me what you're doing. And so I have, this is the time I probably wouldn't do the quotient rule because of this coefficient. 2 times x squared plus 2 to the negative 3/2 power. Because if I had done low D high, I would have run into 0. That's a personal choice, that's just up to you. Are y'all still with me? All right, so I'm going to bring down my negative 3/2, and that gives me negative 3 times x squared plus 2 to the negative 5/2 times 2x. So that gives me negative 6x over x squared plus 2 to the negative 5/2 power. All of a sudden, I have a possible point of inflection. I guess what I would do, I didn't write PIP on my AP exam, but my point of inflection might be x equals 0. Don't call it anything though. In fact, if you don't see a sign change, go and cross that out. Just put an X through it. Okay, if it's not a point of inflection. But I believe it's going to be, if I'm doing a second derivative chart at 0, I don't have endpoints. Before 0, this is going to be positive. And after 0, isn't this going to be negative? And the bottom's always positive. It's the square root of something to the 5th power. All right, so I do say that this is a point of inflection. And they might say, what is the point of inflection? If they actually want the point of inflection, I got to go back and fill in the original. Sometimes they'll say, what's the x-coordinate of the point of inflection? But I got to graph this, so I'm going to find that point anyway. What is my graph? Now, what is the first derivative doing? It should be increasing, decreasing. I don't really need that right now, but that's what it's doing. The original is concave up, concave down. All right, so if I go back and fill 0 into the original, I've forgotten what it was. The original was x over the square root of x squared plus 2. So if I fill in 0, I get 0. Okay? So, oh, and we'll go back up here because I already have my asymptotes in. So now I know I have a point of inflection, no critical numbers. You can find a couple other points, but this graph is concave up and concave down. Is that what I said? Yeah. Okay. Alright, so that was just like one full problem. I feel like someone was trying to like ask a question. Any questions? There's some good examples in 3.6 of just, so do y'all see why I included 3.6 is just everything that you need to know about equations. It's so high in here, sorry to say. So I would suggest maybe not even working problems from 3.6. These examples are fabulous and they're tough enough so you could like work it and change your own answers from 3.6. All 3.5 is what we've done in pre-cal and calculus. I don't think you need to look at it, you can if you want to, but it's setting the stage for limits at infinity. Okay? So any questions about the test?
Are we going to have like limits of like x?
You will not have to take derivatives and
I mean, the
derivatives of exponents and logarithms yet. If I put those on there, you'd have a calculator and you could go math 8 or math 9. Eventually, I've got to teach you how to do that. I'm going to do logarithm before we leave today, maybe. Any other questions? Okay, so I just want to keep throwing this at you. So this is not on the test. Unless you have a calculator, if you see a logarithm or an exponent, I mean, I've already put logarithms on there. That would just throw you off completely if you did that, because we haven't even typed any into the calculator this year. Question?
Can we go over how to like do it on the calculator?
Yeah, let's do that. That may be a better use of our time right now. So let me give you an equation. So let me erase this. I would put this on the test. So let's say if I have f of x is equal to e to the x sine x. See if you can find the critical numbers of that. Let me give you a domain from 0 to 2 pi. And I'll be pulling up my calculator while you get started on it. Make sure you're in radians, especially if you've like been in physics class or something and you've changed it for any reason, or standardized test practice or whatever. Make sure you're in radians. By the way, those of you that are starting, if you still have subject tests to take, and you have questions, I know a lot of you have tutors, but I'd be glad to help you with that, like 100% for free, or even deciding which one to take, but you should all take the math too, so that's decided. Anyway, if you have questions about the topics or a problem you can't work, and you want to ask me, I'll be glad to look at it with you. All right, so first thing I would do is check my mode. And I'm in radians, so then I'm going to go to y equals, and I'm going to clear these. Oh, I'll just leave that there, kind of like that. So I'm going to have sine x e to the x. I think I actually said e to the x sine x, so let me be consistent. Did I have e to the x sine x? Okay, so y'all have that in y1? All right, it could be that I want to turn that off now. Don't forget, if you have this sitting in y2, a lot of times you don't even want to, you want to turn that on or off at will, okay? While we're here, why don't we go on and talk about the second derivative also? So I'm going to go math 8 in terms of x, and I'm going to go to, sorry, I think I was moving too fast. Okay, so vars, y vars function, and I think I want it of what's in y2. And so that would be my second derivative in terms of every x. All right, so I'm going to turn this one off right now. I don't want my first and second derivatives swimming around on the same thing. I'm going to set my window from 0 to 2 pi. And if I'm looking for critical numbers, I may want to shorten that window. There's one I give on the test sometimes, haven't made out the test yet, but there's one in my mind that I give quite often. You've got to really look close to 0 and change your window from like -1 to 1 to act on the y-axis to actually see how many times it crosses the axis. All right, so now I'll graph and hope that this has critical numbers because I just made it up. it goes way far down. I don't know if it's gonna come back up. Is it finished? Okay. So there's my first derivative, which is a lot of what you practice. There's no reason for this to be undefined, so it must go way down somewhere. Darn, I want to pull that in. Where'd my calculator go? Do I have to escape?
Yeah.
Okay.
Or you could try like sliding to.
Yeah.
Yeah.
All right, so I see that my first derivative is positive, negative, positive. I don't want to be looking at what that's doing, okay? My first derivative is positive, negative, positive. I'm going to do calc 0 to find those two numbers. On my plus minus chart from 0 to 2 pi, I've got a critical number here and a critical number here that we will find in a minute. My graph goes plus, minus, plus my first derivative. That means my original's increasing, decreasing, increasing. And they both are going to be one or the other. This one's going to be a relative max, and this one's going to be a relative min. When you report them, you can give 3 decimal places. We've talked about how to store them and fill them back into the original. And we're kind of running out of time, but y'all see what I mean? I would go to second calc 0 and find that number. It was a bonus on the last test. Now I thought you should be able to do it. Second calc 0, find the other one. Then I could turn this off and do a first derivative test, okay? So I'll probably, this afternoon, if I remember, I'll probably write up the answer to this and email it to you, all right? And just go on and start studying, piece it together, see if you have any questions, let me know.